Sodium emission is yellow. But what about potassium? Very different. If you go to rubidium, they all have these very different colors, and all because of the fact that this transition is the one that you're really looking at. And it was two people, Bunsen and Kirchhoff, I think, who actually set the whole idea of exciting these atoms in a flame, looking at their colors, monitoring the wavelengths, and be able to tell what the element is. They were the first, I would say, spectro-analytical chemists. They use spectroscopy for analytical purposes, meaning you excite the molecule or atom in a flame, get the spectrum, and looking at the spectrum, be able to say what the element is. So they were the ones who first devised this idea, and then of course now it's caught on. Now, for those of you who will be doing chemistry and who will be looking at analytical chemistry lab, we in fact have a spectrometer called the atomic absorption spectrometer, with which you will be able to tell what is present in a sample of water or sample of whatever else that you may have, and also tell us how much of it is there. And how much of it is there can actually be measured to the extent of parts per million. That is a few micrograms per ml. And for very favorable situations, it can get down to about 100 parts per billion. That's 0.1 ppm or 1 part per billion. The point is that these transitions are so intense that you can actually use them to measure extremely small concentrations of materials in the sample by using the emission as a probe. Arsenic in water, groundwater, and that's a big issue in many parts of India. And if you look at arsenic, what's the concentration of arsenic? Actually, what should it be? It should be the order of a few parts per billion, which is a few nanograms per ml. Anything higher than that, the sample of water does become extremely toxic and leads to arsenic poisoning. But then how do you measure parts per billion? How do you measure nanograms per ml? Very similar techniques. You excite the arsenic in a flame, it will emit, or you can let it absorb. Look at the spectra of this atom that is being absorbed or emitted, and hence find out what the concentration is. The point again is that these atomic emission techniques or atomic absorption techniques are extremely powerful, extremely sensitive. And of course, if you throw in the laser to go into that, you have so much light that then you start looking at parts per trillion. It's like not nanograms per ml, you're looking at picograms per ml. And I think if you just keep pushing, you don't have to have anything over there, you will still see something in it because the experimental method is so very sensitive. And today you have techniques that can really look at a few molecules or a few atoms in a solution that you might possibly have. Many of them will come back to looking at emission techniques. Okay, now that is basically for hydrogen, but the moment I go to a polyelectronic system, let's say even helium for that matter, what happens immediately? For helium, I need the board to be a little bigger and cleaner, and you will see what. The 1s, 2s, and so on, that those will stay. But what happens to the 2p now? 2p is not going to be the same in energy as 2s. That's only true for a one electron system. Hydrogen, helium plus, lithium 2 plus, carbon 5 plus. It doesn't matter. As long as you have a one electron system, 2s and 2p will have the same energy. 3s, 3p, 3p will have the same energy. But the moment you have a second electron present in the system, the situation is very different. What happens? The 2p has to be higher in energy than 2s, and that's the reason why you fill 2s first and then you fill the 2p. Your Hofbauer principle and things like that, or the n plus n rule, all come in because of a certain hierarchy that exists in the energy level diagram. So you have 2s, and then the 2p is up here. You have 3s, 3p is up here. 3D is up there. And that is going to happen. And now when you start filling up, you fill up this, you fill up this, you fill up this, and therefore you have a certain hierarchy in which you fill up these levels. I'm not wrong. Excepting that, this time there was no boom. Maybe can you just call Rajesh? Tell him that. hydrogen, when I go from, let me see how high I can go up. When I have to go from 2p to 3s, I have to go from 2p to 3d. The 3s and 3d are the same anything else. So how do I know I'm going from 2p to 3s and 2p to 3d? Because there will be just one line. It's like your overtones or like your harmonics in your infrared spectrum. You have to wait till we do Zeeman effect, where we apply a magnetic field on the system and split these levels. And then when you do that, you will see that all these guys will show up as two different transitions. So once we do Zeeman effect, which of course Banwell does Zeeman effect immediately after doing all this. But I won't do Zeeman effect immediately after doing all this. I will do Zeeman effect after I have done NMR. The reason being, I want you to realize that NMR itself is a Zeeman experiment. And whether it is experiment that is done in the radio frequency region, which is what NMR is all about, or whether it's an experiment done in the optical region, which is what this experiment will be, the underlying theme is the same in both cases. In both cases, I'm going to apply a magnetic field, split some levels based on certain rules, and then conduct the transitions. And if I do that, I get a whole lot of information that way. That's what is done in NMR, that's what is done in an optical Zeeman experiment. So when you do that, this degeneracy will completely be split, and you'll be able to say, yes, there is a transition from 2p to 3s, and there is another transition from 2p to 3d, because these two, in the presence of a magnetic field, will not be the same.
The energy of doublet is half the third n, and doublet d half. Would that be the same? I mean, like, yeah, we know that d is going to have some 5 states.
Well, it will have, for a doublet, it will have only 2. Doublet be 3 halves and doublet be 5 halves. That thing on top is 2, you'll only have 2 states over here. In the case of S, you have 1. But they'll be so close, it will be very hard to figure out. But the moment you put a magnetic field, you can tell one from the other. And we will do that at that point in time. I will in fact come back to this problem and tell you how this problem will sort of bothering us. We will go back and look at it there. Okay. Yeah, it's going to be quiet because now we don't have a mic. Now when I do this, and in helium, how many electrons do I have? I have 2 electrons. If I have 2 electrons, and if I have 2 electrons in this, what's the state I'm going to get there? 2 electrons, both in 1s. L will be 0 in any case, because L1 is 0, L2 is 0. They're both 0. Therefore, it has to be an S state. But what about the spins? Should they be this way or should they be opposite? Well, they have to be opposite. And we know that. Otherwise it upsets Professor Pauli in a big way. So it has to be opposite. And if they're opposite, what's the total spin angular momentum for that? 0. If that is 0, it should be a singlet state. And therefore, this has to give me a singlet. I call that a singlet S. And singlet S will always give me a 0J state. If I have both the electrons sitting here, that has to be another singlet. Sure. But then supposing I promote one electron alone to this situation, then what do I have? I have a 1s2s situation. If I have a 1s2s situation, what are the possibilities now? If both electrons are in L equal to 0, 1s L is 0, 2s L is 0, and therefore what is my capital L going to be? 0. And if capital L is 0, what is my state? S state. But if the 2 electrons are in 2 different orbitals, then I have the possibility that they can be like this or they can be like that. Now I don't have a problem with Professor Pauli. They can be this way or they can be this way. If they are this way, what is the spin state now? Singlet, because they are paired. Therefore it must be a singlet. Therefore if I have 1s2s with the electrons like this, then I must remember not to shout after I put this on. Yeah, so if I have a situation like this, what do I get? I still get a singlet S state. Let's say I have 1s3s. Again a singlet S, excepting that the second electron is progressively being pushed to a 2s, to a 3s, and so on. However, if these two electrons in the 1s and the 2s levels can actually stay this way, then what do I get out of that? Triplet. I now get a triplet. So what I'm going to do, you can see the line I have put there. I'm going to go to this side of the board and say that I have a 1s, 2s situation in which the electrons are like this, and if they're like that, I essentially look at a triplet S state. So paired systems are going to give me singlet S, and unpaired but same direction, same spins in a 1s, 2s. I can't get that situation for 1s2. 1s2 is fixed. The only thing that's possible with 1s2 is a singlet S state. But with the 1s, 2s situation, I have the possibility that this state can either be a singlet or it can be a triplet. Right? So all the states that will come on this side will be triplet states, and all the states that come on this side will be singlet states. What's the other possibility? I can excite this to 1s 2p. If I excite to 1s 2p, what is the state I am going to get? L equal to 0, L equal to 1. What is the total L going to be? 1. And therefore what state is that? A p state. And on this side I am going to keep my electrons paired. If I keep them paired, what is the spin state I get? A singlet, because they are going to be this way. They are going to be a singlet, and therefore that's going to be a singlet p state. The same one is 2p. On this side, they go this way. What is the total L value for this? Again, same as that. It's going to be L1 is 0, L2 is 1, capital L is 1. It must be a p state. But what is the spin of this p state? It's got to be a triplet. And of course, I can have a 1s, 3s. Let's say, again that will be a triplet S. I can have 1s, 3p. And again that will be a triplet p. Because at the end of the day, all I am doing over here is keeping one electron in the 1s level and progressively pushing the other electron from a 2p to a 3p to a 4p and so on, but ensuring that the spins are the same for all the states on this side and keep ensuring that the spins are paired for all the states over here. I have both possibilities now, and therefore I am going to get one set of singlet states and one set of triplet states. Now let's see with what I have written, what are the transitions I am going to have. This has to go here. Why does this have to go there? Because one electron is sitting in SS, but what has happened to the other electron? It has gone from S to a P. Therefore, what is the delta L value? 1. I am okay. What is the delta capital L value? That was P and then capital L is also 1. Therefore, that is another selection rule that we worry about. Delta L must be plus minus 1. There is also a 0, we will come to that later. But as of now, let's assume that the selection rule that we have been looking at is very similar to what we learned earlier for rotations. Little l changes by 1, capital L must change by 1. All these are offshoots of this integral that we were working up. So if you know these wave functions, you can actually calculate them. If you know the symmetries, you can calculate them. There is one more selection rule that's very, very important, and that is delta S. And not today, but on Monday, I'll tell you how again symmetry comes into play and causes the delta S to be 0. What is delta S 0 actually telling me? It's simply telling me that if I have a singlet state, I better go to another singlet state. If I have a triplet state, I better go to another triplet state. I can't jump from a singlet to a triplet. Because if I jump from a singlet to a triplet or singlet to something else, let's say a quartet or whatever, then I have a situation in which I am changing my spin. And I can't do that because spin changing transitions are forbidden. It must be a delta S equal to 0, which means I can go from here to here, but I can't jump this and go here. This is a real strong boundary. In other words, I can't have transitions or states on this side wanting to connect with states on this side. Because all these states, mind you, are triplet states. Therefore, any state over there can only interact or only interconnect with states on the same side, provided these two are met. If they are all going to connect with each other on this side, automatically the delta S equal to 0 is taken care of, because we have written on this side all states with the same spin. But if at any time you want to take that state and say I want to make a transition from 1s2 to 1s3s of this triplet, you can't do that, because that has a singlet S designation and this has a triplet S designation. Singlet to triplet not allowed. And therefore you will find that you can't have changes this way. So if I gave you a question in which I said, I will mark some transitions on this and tell me which transitions are allowed and which transitions are not allowed. And if you think they are not allowed, tell me why they are not allowed. And if I gave you a transition like this, the first thing you got to tell me, sorry, that transition isn't going to happen because it is a spin changing transition. Because it is actually a singlet P to a triplet S transition. There is no problem with delta L selection rule for that transition I showed you. There is no problem with the delta capital L selection rule, because that also is delta L is -1. But what is the problem over there? You have a delta S equal to not 0. It's 3 going to 1, therefore it's not 0. And therefore you will find that that transition is actually not allowed. It's actually spin forbidden. And this spin forbiddenness, particularly now the light atom that we are looking at, is very, very important, because it simply prevents certain transitions being observed. It therefore makes life a lot easier. If you didn't have spin changing, if you spin forbidden transitions, just imagine for yourself, this goes here, this goes here, this goes here, this goes here, here, everywhere. You're going to have a very complicated spectrum actually. In fact, that's what happens for heavy atoms. Because heavy atoms, someone decides they're not going to worry about spin selection rules. There's a reason for that. That's why we keep talking about hydrogen and helium. Those are the ones that obey us. And you have all these delta S equal to 0 transition state. You go to heavy atoms. Oh, that will go there. And heavy atom spectroscopy is actually quite horrendous. For the simple reason that many of the selection rules that are actually obeyed by light atoms, heavy atoms don't seem to obey. So you go to electronic spectroscopy, lot more transitions than light atoms. You go to rotational spectroscopy, lines are too close and therefore you can't actually resolve it. You want to do vibrational spectroscopy, too close vibration levels, again that's an issue. So you always find that if you want to do any heavy atom spectroscopy, well, you must want to torture yourself. And you then, of course it's interesting in its own way. There are many people making a living out of studying heavy atom spectroscopy, heavy molecular spectroscopy. But the point I'm trying to make is, all these selection rules we are talking about, just keep in mind, we are dealing with hydrogen and helium and lithium and so on, little babies in the periodic table. But by the time you get to lanthanum and cesium and praseodymium and neodymium, you are in for trouble, because these have a mind of their own. And we will see a little later, when you get to heavy atoms, what the complications are. So I will do a little bit on this on Monday. Then we'll have a little quiz. We'll discuss the quiz, the summarize the course, and we'll stop at that point in time. Two announcements before you go. I might be away. I tried not to do that this time. I know I went away during the exam last time. But again, something has come up. I might have to leave on Tuesday. If I do leave on Tuesday, then of course, I'm not around for the entire week. Somebody else, maybe I'll ask Ramesh to help me with the exam. But if you have questions to ask of me, please do it by Monday. I'm available over the weekend. I'm available on Monday. Please come back and ask me questions. The other announcement is, there's a Curie Club meeting tomorrow where new faculty in chemistry, Dr. Sukumar, will be talking on medicinal chemistry and aspects of antibiotics, synthesis and so on. So it would be nice to come over, because I need to talk to you about industrial applications of organic chemistry.